Spiders! They're creepy, they're crawly, have 8 eyes, and are in general not too nice to look at. Surprisingly, there has been quite a bit of research done on this arachnid in the past years. This is because of the amazing natural mechanical properties of its silk. They're spun by spider spinnerets. They use their silk to make webs or other structures which function as nets to catch other animals, nests to protect their offspring, and a method of suspension and as transportation. Yes, I do mean it. The method of transportation is called ballooning. They extrude several threads into the air and let themselves be carried away by the wind. The extremely fine silk that spiders use for ballooning is known as gossamer. There are many different kinds of silk: dragline, flagelliform, cylindriform, aciniform, minor ampulate silk, and piriform silk. Each type of silk has a set of mechanical properties optimized for its biological function, and most silks, in particular dragline silk, have exceptional mechanical properties. Spider silks exhibit a unique combination of high tensile strength and extensibility. This enables a silk fiber to absorb a lot of energy before breaking. This specific material property is known as toughness. A frequent mistake made in mainstream media is to confuse strength and toughness when comparing silk to other materials. As you can see here, weight for weight, silk is stronger than steel, but not as strong as Kevlar. Silk, however, is tougher than both. The toughest known spider silk is produced by the Darwin's bark spider. It is over 10 times tougher than Kevlar. This is quite amazing because this level of toughness rivals that of the highest quality modern polymer fiber that can be produced in labs today. In addition to toughness, spider silk's low density contributes to its interest as well. The density of spider silk is about 1/6 that of steel. As a result, a strand long enough to circle the earth would weigh less than 500 grams. Spider silk is also extremely ductile, so much so that it can stretch up to 5 times its relaxed length without breaking. Finally, spider silk is also incredibly resistant to change in temperature. While unlikely to be relevant in nature, dragline silk can hold their strength below -40 degrees Celsius and up to 220 degrees Celsius. As you can see, spider silk has some amazing properties, the uses of which would be endless. The process for creating spider silk is also non-polluting. As such, using spider silk would be a more ecologically friendly method of creating fibers used in applications like bulletproof clothing, wear-resistant lightweight clothing, ropes, nets, seatbelts, and parachutes. Researchers have also been looking into methods of using spider silk for biodegradable bottles, bandages, surgical thread, artificial tendons or ligaments, and supports for weak blood vessels. Unfortunately, at the moment, producing spider silk is an economy of scale. It is very hard to get the resources to do so, and once gotten, the amount of spider silk that can be produced is much less than if an actual spider made it. In addition, some of the processes to make the artificial spider silk create spider silks that are a lot less strong than actual spider silk. Originally, getting spider silk in large quantities was achieved by harvesting silk individually from each spider in a large group of thousands of spiders. This is extremely inefficient, so recently researchers have been developing alternate methods for creating synthetic spider threads. One Canadian company, Nexia, has successfully produced spider silk protein in transgenic goats that they have genetically modified. The milk produced by the goats contains significant quantities of the protein, 1 to 2 grams of silk proteins per liter of milk. Using a wet spinning process, they squeeze the silk protein solution through small extrusion holes in order to simulate the behavior of spinnerets. Unfortunately, so far this procedure has been unable to completely replicate the properties of native spider silk. In addition, other researchers have explored multiple other ways of developing synthetic spider silk. For example, researchers from the Korea Advanced Institute of Science and Technology have succeeded in making spider silk directly using the bacteria E. coli. This specific process allows the manufacturer to create silk in a much more cost-effective manner. Another method that has been developed by Craig Biocraft Laboratories is using silkworms that have been genetically modified to create the spider silk protein spiruline. So far, they have been successful in production, and right now they are trying to increase their production rate. If I had more time to research, I would love to look into why the macroscopic and molecular structure of spider silk gives it its mechanical properties, as well as a history on the research and development of synthetic spider silk and transgenic organisms.